All right, so welcome back. Today in this video, we're going to be looking at mechanics of materials, and this is the first section of this review for mechanics of materials, and we're going to be specifically looking at shear and moment diagrams. So we're going to be drawing a little bit in this section, placing our forces, looking at external forces, and just being really interactive. So I have some practice problems for you all, and I'm going to be going over some concepts that you will need to know for your civil FE exam. All right, so let's go ahead and get started with number one. All right, so number one says, given the following, AX is equal to 0, AY is equal to negative 10 kilonewtons, BY is equal to 55 kilonewtons. Find the shear force at point C. Okay, so let's look at this. What information are we given? Well, we're given, if I just look at this diagram, it looks like we're given some external forces or reactions along this beam. Okay, so we are given reactions. Okay. And we're trying to find the shear. Goodness gracious. Handwriting is horrible. Shear force. Okay. So we're looking for shear force at point C. All right. So let's go ahead and label our external forces. So we know this is equal to 0. The AX is equal to 0. AY is negative 10 kilonewtons. All right. Okay, so it's coming down negative 10 kilonewtons. My BY is coming up 55 kilonewtons. And I think those are all the forces. So if we want to make sure that this is balanced, you could do sum of the forces in the y direction is equal to negative 10 kilonewtons coming down. I have another, it's coming down 5 kilonewtons per meter over a span of what, 4 meters. And then I have my BY coming up at 55 kilonewtons. And we have one more force acting at point D, coming down at 25 kilonewtons. And when I add all these up, I get 0. So I know that this is balanced, right? This is a balanced beam. Also, the sum of the forces in the x direction is equal to 0. And the only forces could be potentially there is AX, and that is equal to 0. So, all right. So what is shear force? Gotten that this beam is balanced, but what is shear force? Well, shear force is basically just the force that's acting on the beam at a particular point. So it's asking what is the force that is acting on the beam at point C. Okay. So we can draw this, all right? And if we look at shear, we go to shear and moment diagrams. This is what we're kind of in. All right, so the handbook tries to show us how to do shear and moment diagrams, saying positive shear, negative shear, but this doesn't really help us. So I'm gonna go over it. So basically, shearing force is positive if the right portion of the beam tends to shear downward with respect to left and right. So a positive shear is going up. Negative shear is going down. Okay. Positive shear, and this is negative shear. Similar to a force, right? Got force, if it's coming down, we treat it as negative. If it's going up, treat it as positive. All right. Okay. So let's look at, we're going to draw a shear diagram, and the shear diagram just basically is where you redraw the beam, and this line, this black line that I'm drawing, is the shear along the X direction. So you're going to have your point C, which is what we're looking for the shear at. You're going to have B, just what we're not looking for. Got point D at the end, and you got point A. Right. Okay. So what's the force at A? Okay, so we got the force at A. It is coming down at -10 kilonewtons. Right? And it's important to note, this is our negative, that's our line for our -10, right? So if I was to come down further, it might be -20 kilonewtons. But in this case, since our force at that point is -10 kilonewtons, then that's what our shear is at that point. All right. And it's important to note that your shear stays constant if no other forces are acting. So between here and here, right, there's no other forces that take place on it. So our shear is going to stay at -10 until point C, right? And even at technically at point C, it is -10 kilonewtons. So in this particular example, we didn't put negatives or positives, but technically this would be a negative, should be a -10 kilonewtons. But all in all, definitely 10 kilonewtons. Okay, so now we've gotten to point C. What happens next? I'm just going to take you through kind of the whole scenario. So how do we find the shear from C to B? So let's look at shear C to B. And that is going to be equal to, well, we know at C, we're at -10 kilonewtons, but it keeps coming down, right? So from C to B, we are continuing to go down 5 kilonewtons per meter. And then we multiply that over our 4 meters. Okay. So this is 4. All right. So the shear from C to B is going to equal -30 kilonewtons. All right. So what this is saying is okay, the shear was -10 until we started at point C. Then we gradually kept going down another. We went from -10 to this point is -30 kilonewtons, right? That's what happened here from C to B. Okay, now at point B, we have this big jump. So shear at B is equal to, we're at -30, but what? We have this positive 55 kilonewtons, right? So V shear at B is equal to 25 kilonewtons. That means when we bounce, right? So if there's a force coming up, it's going to take us all the way up to 25 kilonewtons. And it stops. All right. So then we continue. There's no other forces acting, so we continue from left to right. And then what happens at the end? Well, it's important to note it should always come back down to 0. And so we're at 25 kilonewtons and we have a force that brings us back down at D to our 0 point. So yeah, we're back to 0. So this is what our shear diagram looks like. And it's important to note that the area underneath this is like level 2 stuff. The area underneath is your moment. You're going to use that for moment and max moment, stuff like that. Right now, we're just looking at shear, so our answer was B. All right, let's look at number 2. All right. Number 2 says, where does the maximum bending moment typically occur on a simply supported beam with a concentrated load? All right. So we're given that we have a simply supported beam. And we want to know, and there's also a load that is concentrated. And we want to try to find where max bending moment occurs. All right. Are there any formulas that we need for this? So I would look up simply, maybe supported. I don't simply supported. Simply supported. Something comes up. All right, this table comes up. Now we have a concentrated load. This is simply supported. And typically what simply supported means, this is just for your background, is that it simply supported just means that it's very simple. You have a beam and you have a pin on one side. It's my pin. and then a roller on the other side. That's all simply supported means. Supported by two different types of supports, a pin and a roller. Okay. The next thing we need to make note of is, where does the maximum moment happen? And in this table, it lets us know that the maximum moment or concentrated load happens at the center. Okay, so our choices are at the left support. So that would mean our max moment would happen at the left support, which technically would be here. So that's wrong. So I know that at the left support, okay, if we're talking about at the right support, it would be here. That's wrong. That's not where your max is going to be. Well, this one looks like it could go either way. And so, I'm looking at this, and as I'm going through, at the right support, so we know that's wrong. But let's look at our other two choices. At the center of the beam, well, if the concentrated load is at the center, like this, let's just say our point is at the center, then yes, that's where our max happens, right? But it doesn't, they don't give us where this load, it could be at the center if that's where the load is. But if it is located somewhere else, like in this box here, says the maximum moment is located at point of load, which is, that's the point of load. So wherever the location of that point of load is, then that's where the maximum moment could be. So it is either C or D in this case. So we had two correct. I'm just going to put answer C or D. And I'm just literally using these diagrams to let me know where the max is. I really believe though that, yeah, it literally could be either one. And by using the pictures, it helps. All right. So P is your point load, knowing that there is a pin, there is a roller, making sure that you're in the right areas. It says simply supported beams too, which helps. But yeah, for this one, it could be C or D. All right, let's look at number 3. All right, so given the following, AX is equal to 0, AY is equal to -10, and BY is equal to 55 kilonewtons, find the moment at point C. Okay, so this is a similar question to the one that we had, right, for shear, but this time it's asking us for moment. So we're given our reactions. We're trying to find the moment at point C. Okay, so what we need to do to determine moment is just going to be the area underneath the shear diagram, right? Or you could say it's the force at that point times the distance. All right. So let's look at the diagram. Let's do it the diagram way. So I'm just going to say we had our shear here, right? It's not really a straight line, but actually I'll redraw it. See if I can draw a straighter line. It's a little bit better. Okay. So we said that this is v of x, right? We also said that our force was coming down -10 kilonewtons, came over to point C here, and then it continues. So what's the area at point C? A, this would have been B, this would have been D. So it's always, what's my distance, right? Well, my moment is equal to my force times my distance. Moment is equal to, I was at 10 kilonewtons, so negative, times, what's my distance? Well, it's distance 2 meters. So my moment underneath, or the underneath the shear in the shear diagram is going to be equal to -20 kilonewtons per meter, or dash meter, kilonewton meters, and that is going to be D. So very important as you're looking at shear and moment diagrams, you can determine them based upon the area underneath the shear diagram. So another thing to take note of, and I'm just going to look at to make sure that this is right, but I think the manual does help us diagram. See if anything comes up. See if shear diagram comes up, and it can save us some time. Wait. Nope. 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 All right, that's not helping us. So shear, search shear again. See if we can get in the right. And you can always use your bookmarks as well to get you in the correct area. All right, so this does help us determine certain things. So you know if you have positive bending moment, so positive bending is typically concave up, that. And if you have negative bending, it's concave down. Okay, so I got the moment, I found the moment at the point, but the diagram, if I drew it at the diagram, right? If I have a negative, so you draw your shear diagrams, your moment diagram is very similar. So you just put m of x, right? This represents 0, that line. You have point A, C, B, D. You can't see anything. All right. Having a little difficulty here. So what I'll do is I'll draw our moment diagram, maybe up above. Or get rid of some of the stuff. I want you to be able to see this. Okay, so similar to your shear diagram, you're going to draw your moment diagram. All right, and if concave up is positive bending moment, and concave down is negative bending moment, and that's what the handbook says right here, then what would this like the look of from A, what would the look of the moment be from A to C? Well, we have negative. We're having a negative moment, correct? So it'd be a concave. Since this is constant and it's constantly negative, it's going to be like this. Right? And that's going to be our negative 20 kilonewton dash meter. All right, so it's straight. So if it's constant, it's constantly going down, right? But when does it curve like that, right? Well, it will curve as we have a gradient here, right? So when I mean gradient, by gradient, I just mean it decreases over time, even more negative, right? So it's going to be like this. There's going to be even more negative moment. So it's just a little bit of a curve, but you just want to keep in mind that your moment is going to be negative or concave down when your shear and moment, or your shear is negative, and if your moment is positive, then it's going to be, concave up. So just some things to think about there. All right, so this concludes the shear moment diagram section. If you know this information, you should be good on your exam. You just want to be able to visually know what's happening. If they're saying, okay, we have a max, what would the max moment or max bending moment be if you have a simply supported beam, right? Like on number 2. What does negative shear and positive shear look like? What does negative moment and positive moment look like? So mastering those key things will allow you to make sure that you're ready for this portion of the exam. All right, so let's go to our next section. The next section, we're going to be looking at stresses and strains. So I will see you in the next video.